Hello everyone, please let me know if I am completely audible and visible to you. Anyone please drop a comment if I am completely audible and visible so that we can start. Okay, so today we are going to start with the binary index tree, or you can say this Fenwick tree. Okay, but before that we'll be doing what we always do, that is taking a recap of what we have done till now, and then we'll be starting. Okay, so please drop a comment if I am completely audible and visible. Anyone? Okay, okay, so let us first discuss what we have, what we have discussed till now. So the first point is, first we have discussed about the prefix structure in the series of the advanced data structure. First we have discussed about the prefix structures. Okay, after the prefix structures, like in the prefix structures we have discussed about these things, that is the 1D prefix sum, say prefix sum or prefix or anything like prefix structures, and then we have discussed about the 2D prefix structures. And after that, in the series we have discussed about the square root decomposition. Okay, and then by using the idea of square root decomposition we have discussed about the Mohs algorithm, and we have also solved an interesting problem on the Mohs algorithm. Okay, and what we were discussing about the range query structures, and today also we are going to discuss one more range query structure. So we were discussing about the range query structures. Okay, and the next thing in this series that is we are going to discuss today is the fourth topic, that is Fenwick tree, and sometimes it is also called as the binary index tree. Okay, so before starting with this, we would be taking a problem statement, and the problem statement would be the same that we have discussed for the problem statement would be the same that we have discussed for exploring all the data or the possible data structures. We would be given an array. We would be given an array. Suppose this is our array, and we would be having n elements in our array, that is 0 1 2 3 4 5 6 7 8 9 10. Consider any number of elements. Okay, so you are given an array. So suppose this is array A of n elements. Okay, and again we would be given q number of queries. Okay, we would be given q number of queries, and all the queries would be of type sum L to R. Okay, so we have to find the sum of all the elements which falls in this range, that is al plus 1 up to ar. Okay, so this is what this type of query means. So this is the type 1 query, and the type 2 query would be update. Okay, so the type 2 query would be update, and by update I would be passing two things, that is index and x. So this query means that we have to update the element that is present at the index I and d by a value of x. Okay, so these two operations we have to perform, and this query is not the online queries. Okay, so not the offline queries, sorry. So this is the online queries, and if these queries are online, definitely we cannot apply the Mohs algorithm here. Okay, so these queries are online, that means we can get any heterogeneous set of the queries. Like suppose if we are given 6 queries, so this can be like this one and this. Okay, any set of queries, like any possible sequence of the queries we can get. So before processing any ith query, we have to first calculate the result of the I minus 1th query. Then and then only we can go to this query. So this ith query. Okay, so this is what the online query means. Now, what is the best possible solution till now we have discussed for this kind of problems? Okay, so the best possible solution that we have discussed was the square root decomposition technique. Okay, so this square root decomposition technique was the best technique we have discussed till now to solve n queries. Like q is always comparable to n in most of the problems. So like I am considering the q number of queries is equivalent to n. Okay, so in that case, what is the best time complexity I have ever achieved? So for this kind of problem where we are getting two types of queries, one is sum and the other one is update, and the nature of the query is online. So for that, whatever data structures or the techniques we have studied till now, the best technique was the square root decomposition, and that was n root n. Okay, root n to process each query, root n to process each query. Okay, and n, if n is the number of queries, so that would be n root n would be the time complexity. But now the technique which we are going to use today, or say the data structure which we are going to use today, that is the bit or binary index tree, is guaranteeing me the best time complexity. Okay, it will guarantee me the best time complexity, and it is much better than this time complexity. We are going to discuss that too. Okay, so this is the precap, and like now let us deduce that, like we are going to do the how we are going to do or store the elements in the data structure. Now let us discuss that. Okay, so suppose if we are given an array, and again if this is our array, and suppose these are the indices. Someone is saying segment trees. So not segment trees, we are not going to discuss segment trees in the today's lecture. Definitely we'll be discussing about the segment trees later on in this series, but today we are going to discuss about the Fenwick trees or the binary index trees, which has the same time complexity as the segment trees, but it is still better. This binary index tree is still better than the segment trees, because the implementation or the code is smaller, and like it takes less space. So that is also we are going to discuss. I think Ankur Rai has commented this. Okay, so suppose these are the indices. Okay, now suppose if we are asked the query of sum L to R, then what we can do? So suppose if we somehow can calculate the sum of uh, if we somehow can calculate the sum of 0 to R, and then if we subtract the sum of 0 to, then we can subtract the sum of 0 to L minus 1 in this to get this result, that is sum L to R. Okay, so we can definitely do this. Okay, now what is our target? So our target is to find this particular sum. Like we have to find the sum of all the possible indices, like the sum of 0 to I for all I uh, greater than 0 to less than n. Okay, so this is our target. We want to find the prefix sum of all the indices. Okay, and this prefix sum is not the static prefix sum. This okay, Ankura is commenting something, like he is suggesting that we can use the segment tree as a data structure. Yes, definitely you are correct. Okay, but this is out of scope for today's discussion. We would be discussing that later. Okay, now so what we are talking, so we were talking that we have to calculate the prefix sum of all the possible indices, but the prefix sum here is not static. It is not static. Okay, the prefix sum here we are calculating would be dynamic. Okay, what do we mean by dynamic? By dynamic, I mean it is also able to accommodate the updation that is made to the array. Okay, so if we are making the static prefix sum, in that case if we are doing some particular updates, so that update is not reflected in the prefix sum, and to reflect that particular update, we have to always say update the prefix sum array also manually. So definitely that is a time waste, or like that is not efficient. We would be maintaining some kind of dynamic structure, dynamic prefix structure here, and we'll be using that dynamic prefix structure to solve this type of queries. Okay, so I think the idea is clear that what we are going to do. Please say yes or no if the idea is clear. Like, I haven't explained yet anything, but if the idea is clear to you, just drop a comment. Okay, now suppose, so now let us try to come up to the algorithm, like what we can do. Okay, now suppose if I have to calculate the sum of 0 to I, okay, or say to be more specific, say sum of 0 to 5. Okay, then the naive, what we are doing naively, so in the naive approach we are pointing our fifth element. Okay, so we are putting our pointer at the fifth element, and we are taking the sum of a5 plus, we are reducing our pointer to this particular point, and we are taking the sum of a4 plus, then we are reducing this and we are taking the sum of a3 and then a2 and then a1. Okay, so then a0. So this thing we can do naively. Okay, and for this the processing of each query would be order of n. Okay, so so this was the naive approach, and if we were using the square root decomposition, what we can do, we can reduce the number of steps, because in that case we can divide the array in some smaller number of chunks, and we can just process the array. And now suppose if we want to calculate this sum of 0 to 5, what we can do, instead of calculating this sum, we can just calculate the block 1 plus block 0. And what would be the block 1 and block 0? So suppose this is block 0 and this is the block 1, so we have to just take the sum of these blocks. Okay, so we'd be putting our first pointer here, we'd be taking the sum of this particular block, and this would be computed, and then we would be taking the sum of this block. Okay, so here we have reduced the number of operations. Okay, and the time complexity for processing each query in this type of case was order of square root of n. Now what I want to do, or what I want to achieve, I want to achieve a better time complexity than this one. Okay, and the better time complexity from this one, that is the order of square root n, is the order of log n. So this is definitely a better time complexity than square root of n. Okay, we can like prove it also. For example, if n is 10 to the power 6, then if you take the square root of this, then if you are taking the square root of this, the square root of this comes out to be 10 to the power 3, and if you are taking the log base 2 of this comes out to be something around 20. Okay, so you can see the huge difference if we are consuming the square root of n time, or if we are consuming the log n time. There is a huge difference, like of the order of 100. So this matters a lot. So now let us try to come up with a solution that can do this type of queries, like this prefix queries. Okay, that can give me the sum 0 to I in just log of n time. Okay, in a dynamic structure, that means along with the updation also. So here we can see that this is log base 2n, and what do we mean by log base 2n? So it suggests us that we should use bits. Okay, so if we were using the bits in that case, okay, if we are playing in terms of bits, then and then only we can achieve the this logarithmic time complexity. Okay, now how we can do this? Okay, if this is my array, now how we can do this? Okay, these were my indices. These were my indices. Okay, and some element would be stored at these indices. And now I suppose if I have to calculate some 0 to 5, now what I can do, so every number, as we know that every numbers can be represented in terms of bits, okay, or say in terms of in as a sum of powers of 2. Okay, like suppose if I am talking about 10, then 10 can be written as 2 to the power 3 plus 2 to the power 1, that is 8 plus 2 is 10. And suppose if we are talking about the 5 can be written as 2 to the power 1, 2 to the power 2 plus 2 to the power 0. Okay, so that is 4 plus 1 is 5. Okay, so every number you can write as a power of 2. Okay, as a sum of power of 2. Okay, now what we have to do is we have to consider this the lowest significant power of 2, or you can say that you have to consider the lowest you can say that you have to consider the lowest significant power of 2, or the lowest significant bit. Okay, so this is the least significant bit. Now here the least significant bit is 1, say 2 to the power 1, or say least significant power of 2 is 2 to the power 1. So in the 2 to the power 1 is nothing but 2, and 2 to the power 0 is nothing but 1. So so we would be maintaining a bit array, and what we would be storing in each indices of the bit array, that we are going to discuss, and how we are going to use this particular array to get our result. Okay, so suppose that this is my indices. Now at each indices, now suppose if I am talking about bit of 10, okay, if I am talking about bit of 10, so what would be stored in the bit of 10? So it would be storing the sum of two elements, and which two elements? So that is nothing but the 10 minus 2 plus 1, that would be 9 and 10. Okay, it would be storing the sum of elements which is present at the ninth index and the 10th index. And similarly in this manner we are going to store, like if we are talking about the bit 8, so the bit 8, so 8 you can represent it as 2 to the power 3, so it would be storing, so this would be the least significant power of 2, so that is 8, so it would be storing the sum of 8 elements, that is starting from 1 to 8. So at bit 8 we would be storing the sum of 8 elements. So like using this thing we can store something at every index. Okay, we can store the sum of some elements at every index in the bit array, and then we are going to use this bit array to calculate sum. Okay, now we can assume it in a form of tree, and how we are going to calculate this, we are going to discuss that too. Okay, so let us try to deduce a Fenwick tree. Okay, so we can assume this bit array. Okay, so we are maintaining a bit array. Suppose if we are maintaining a bit array for 8 elements. Okay, so 8 elements, so generally we take the size as one more than the required. So suppose if this is my 0, this is my 1, this is my 2, this is my 3, this is my 4, this is my 5, 6, 7, 8, 9, 10. Okay, we don't need that much, we just need 8 elements. For 8 elements we just need array of size this much only. Okay, now we can, like if we are visualizing in terms of array, then it would be little difficult. Let us visualize it in terms of trees, in term of tree. Okay, now what we are going to do, so this generally we consider this 0 as a dummy bit. So suppose if this is 0 and the child of 0 consider as 1, so suppose this is 1, this would be your 2, this is your 3. I would be telling you that how this comes. This is 3 and this is, okay, this is 4, so this is 4, this would be your 4, this would be your 5, this is your 5, this is your 6, and this is your 7, and at last this would be your 8. This would be your 8. Okay, so the thing I am encircling is the indices of the bit array. Okay, so these are the indices of the bit array. Okay, so these are the indexes of the bit array. Now you can, like, for 0 1 2 3 4 5 6 7 8, you can write the least significant power of 2 for each one of them, that is 2 to the power 0, 2 to the power 1. Here it would be 2 to the power 0, here it would be 2 to the power 2, here it would be 2 to the power 0, here it would be 2 to the power 1, here it would be 2 to the power as it is odd 0, and here it would be 2 to the power 3. Okay, so this thing matters, that is the power. This particular thing matters, like 2 to the power 0 is nothing but 1, 2 to the power 1 is nothing but 2, 2 to the power 0 is nothing but 1, it is 4, it is 1, it is 2, it is 1, it is 8. Okay, so blue numbers blue numbers tells us that how many, like, what is stored at the bit 8th position. So the bit 8 would be storing the sum of 8 elements, the bit 7 would be storing the sum of 1 elements, the bit 6 would be storing the sum of 2 elements, and where it ends, so it ends at this index only. Okay, so like bit 8 would be storing the sum of 8 elements which ends at 8. So this is what we can say. So suppose if we are talking about this 8 element at 8, if we are talking about the bit position, so at this index, like this index, the bit of 8, what would be stored at the bit of 8? So if we are talking about the bit of 8, so the at bit of 8, it would be storing the sum of 8 elements, which is like the ending index of which is nothing but 8. So it would be storing the sum of 8 minus 8 plus 1 to 8. Okay, so that would be 1 to 8. So it would be storing the sum of elements from 1 to 8. Okay, so this is our bit array. We are already given an array A, that is 0 1 2 3 4 5 6 7 and 8. That would be that would be having 8 elements. So we are already given an array A, and on this array A we have created a array bit, and that we are going to use to answer our queries. Okay, and then we were discussing that at what index of bit what thing would be stored. So at the index 8 of this bit array, we would be storing the sum of all the elements from 1 to 8, and how we are storing this, we are going to discuss that too. Okay, so and similarly at the 7th index, so this is about the 8th index. Now let us start from the first itself. Okay, so the at bit 1 we would be storing the sum of 1 elements, so that would be 1 to 1, so it would be storing the sum from range 1 to 1. Okay, at the second index it would be storing the sum of 2 elements, so it would be storing the sum of 1 to 2. Okay, and here at 3 we have to store only the sum of 1 elements, that is nothing but 3 to 3. It would be storing this range, the sum of this range. And at 4 we have to store the sum of 4 elements, so it would be storing the sum from 1 to 4. Okay, and at the index 5 it would be storing the sum of 1 element only, so that would be from 5 to 5. Okay, and for 8 we have already discussed. For 6 it would be storing the sum of 2 elements, that is nothing but 5 to 6. Okay, it would be storing the sum of 5 to 6, and the 7 would be storing only the sum of only a single element, that would be 7 to 7. Okay, it would be storing this range. Now we have created it in a form of tree, and we have already stored like what range of sum it would be storing. Now suppose how we can query sum of I in this. Okay, now let us analyze the time complexity. We are not discussing yet how we are going to create that tree, but we are assuming that this tree is already being created. Now how we are going to query on this tree? Okay, so we are considering that this tree is already being created. Now if this tree is already being created, how we can answer our queries? So we would be getting queries of this type: sum of L to R. Okay, and we would be distributing this query as sum of 0 to R minus sum of 0 to L minus 1. Okay, so how we are going to calculate the sum of 0 to R, or we can say in more generalized term, how we are going to calculate the sum of 0 to I. Okay, so that we have to discuss. So suppose, for example, if we are taking I as sum of 5. Okay, now suppose if we are taking I equals to 5, in that case we have to like calculate the sum from 0 to 5. So how we are going to do this? So suppose if we want to calculate the sum of 0 to 5, we will visit the node which is present at the 5th index. Okay, at the 5th index. So suppose if we are talking about this index. Okay, if we are talking about this index, so this index is storing the sum from the range 5 to 5. So it is storing the sum of the range 5 to 5. Now from this point we'll go to its ancestor. Okay, from this point we'll go to its ancestor, and the node number 4 would be its ancestor, and which sum it is storing. Here at the root the 0 would be stored. So which sum it is storing? So it is storing the sum of the range from 1 to 4. So that would be the sum of 1 to 4, and then from this point we will be moving to its ancestor. So its ancestor is nothing but this point. Okay, that is 0, and that is the index 0, and at index 0 the 0 is stored, so we'd be adding it with 0. Now if you combine these two ranges, that is sum of 1 to 4 to sum of 5 to 5, we would be getting the sum of 1 to 5. Okay, or so it is not sum 1 0 to 5, it is sum 1 to 5. Okay, suppose the indexing is 1 based. Okay, so we'll achieve our target by like, so if you want to, we can generalize it. We can take one more example and then we will be generalizing it. Okay, now suppose we have to calculate the sum of 1 to 7. In that case what we can do, now suppose if we have to calculate the sum of 1 to 7, in that case what we can do, we can go at the 7th index. So this would be our 7th index. At 7th index the sum of 7 to 7 range is stored. Okay, now from this point we would be moving to its ancestor. So this would be its ancestor, that is the node number 6, or say bit of 6. So at this the sum of two elements is stored, that is from this 5 to 6. So the sum of this range is stored. Okay, now from this point we would be moving to its ancestor. So the ancestor of the node number 6 would be the node number 4, and at the node number 4 the sum of 4 elements is stored, that is from sum 1 to 4. So the sum of this range is stored, and from its from 4 we would be moving to its ancestor. Okay, so its parent, or say its ancestor, is this 0th node number. Okay, and 0th node number, the 0 is stored, so we would be adding 0 here. Okay, so if you concatenate these ranges, so this would give me a result of like sum 1 to 4 to 5 to 6 would result me the sum of 1 to 6, and then from there if we are adding this we would be getting the sum of 1 to 7. Okay, and this is what we are requiring. Okay, so by doing this we can get back our result. Okay, and what could be the worst case time complexity? So suppose for this, if we are analyzing the worst case time complexity, if we are analyzing the time complexity, or say the worst case time complexity, so that would be the height of the tree. And in worst case the height of tree would be, as it is binary index tree, the height of the tree would be log 2 base n. So that would be the time complexity for processing each query if we are maintaining this particular binary index tree, or if we are storing our data in this data structure, that is bit. Okay, and how we are getting the height of tree as log base 2n, or how we are getting this time complexity, we are going to discuss that too. Okay, so now suppose if you like how you are getting your parent, so first we have to discuss that. Okay, so suppose if I am talking about 7, so we know for 7, okay, now let me clear this thing and then we'll be discussing that. Okay, let me clear something. Okay, now suppose if we if we analyze the parent, so suppose if we are talking about the 7 and if we write 7 in terms of bits, or if we write the binary representation of the 7, so that comes out to be 1 1 and 1. So this would be binary representation of 7. And if we look the binary representation for 6, so the parent of 7 would be 6. Okay, and the binary representation of 6 is 110. And if we check the parent of 6, that is 4, and the binary representation of 4 is nothing but 100. Okay, and if we look the parent of 4, so the parent of 4 is the index 0, and index 0 is nothing but if we take the binary representation of this would be 000. Okay, so we can take one more example. Suppose if we are talking about the 5. Okay, so if we are talking about the 5, for 5, if the binary representation of 5 is this, and if we are talking about its parent, so the parent of 5 is nothing but 4, and the binary representation of 4 is nothing but 100. Okay, and if we are talking about the binary representation of, if you are talking about the parent of 4, the parent of 4 is nothing but 0, and the binary representation of 0 is this. And now suppose if we are talking about 3, so the binary representation of 3 is 0 1 1, and its parent is 2, and the binary representation of 2 is nothing but 0 1 0. And if you are taking the parent of 2, it is nothing but 0. So the binary representation of 0 is nothing but 0 0 and 0. Now you can observe, you can take all the examples, all the possible examples, we have taken 3, and you can like you know that the parent of this is this one. Okay, we know that the parent of this is this one, and the parent of this is this one, and the parent of this is this one. Okay, now we can analyze a pattern here. We can, if we are at index x and if y is the parent of x, then we can get y from x by unsetting the rightmost set bit, Okay, so we can observe that too. So suppose if we are talking about the 7, the 7th parent is 6, and how we can achieve this 6? By unsetting this bit. Okay, suppose if we are making the rightmost set bit as 0, then we would be getting 110, and that is nothing but the parent of 7. And now suppose if we are talking about 6, the parent of 6 is nothing but 4, and how we can get 4? By unsetting this rightmost set bit, that is 0. If you are making this bit 0, you would be getting 100, and that is the parent of 6. So the parent of 6 is 4. You can observe it. Okay, and now suppose if you are talking about the parent of 4, so the parent of 4 you can get by unsetting this particular bit. If you are unsetting this particular bit, we can come to this point, that is 0 to 0 0. Okay, so yes, you can say that you can get the parent by unsetting the rightmost set bit. Okay, you can observe it at this point also. Okay, so here if you are talking about the 5, the parent of 5 is 4, and how you can reach to 4 from 5? So by unsetting this rightmost set bit, you can reach to this point, that is 4. Okay, so that's why the parent of 5 to 4, and we have already discussed the parent of 4 would be 0. How? By unsetting this particular bit. Now suppose if we are talking about this particular example, so what is happening in this particular example? This is 3, and the parent of 3 is nothing but 2, And how we can reach from 3 to 2? By unsetting the rightmost set bit. So this is the rightmost set bit, and if we are unsetting this, that is we are making this bit as 0, so this would be 0 1 0, and that is nothing but 2. Okay, so from this conclusion, from this example, what we can conclude? We can conclude that if x is the child and if y is the parent, we can always reach to y by unsetting the rightmost set bit of this x. Okay, so this we can do. Okay, now we were discussing about the time complexity. Now the time complexity would be more clear to you. Okay, so now the time complexity would be clear to you. Now if you are at any index I, and if you for the index I you would be always ending up to index 0, because 0 would be the final parent for each node, and from I you have to reach to 0, and in between you would be encountering many nodes. Okay, so how many number of nodes you could encounter in between would be your time complexity. Okay, so in worst case you would be getting something like this. Okay, in worst case you would be getting something like this, and you would be unsetting each set bit. So you would be making this 0, and then you would be making this 0, and then you would be making this 0. So what would be the worst case? So this is the worst case. And suppose if the AI is lying in range 10 to the power 6, in that case it would be consuming 20 bits. So in worst case you have to unset all those set 20 bits. So you can like from this conclusion, from this particular test case, you can you can get the intuition of the time complexity, that the time complexity is the order of log n, because that the log n base 2 would be the maximum number of bits a number can have. Okay, so this is how we are able to achieve the log n time complexity for each query in the binary index tree. Okay, anyone having any doubt till this point, like whatever I have explained? Anyone, please drop a comment, otherwise we would be moving forward. Now our target is how we are going to unset the rightmost set bit. So this is our target, so we'll be doing this. Okay, okay, so suppose if we are talking about find parent, so this is our operation, find parent. How we can find the parent? So this is suppose if we are talking about the x, we can take the 2's complement of x, we can take the 2's complement of x, and we can subtract like, if say we can take the 2's complement of x and say if the 2's complement of x is y, then we would be subtracting y from x, and the result would be parent. Okay, or say more generalized, I can mention the steps also. Okay, so we can mention this step. So we can mention these steps for finding parents. So the first thing is, so if you want to find the parent of x, in that case we have to first take the 2's complement of x, take 2's complement of x, okay. Then second step, take and say take 2's complement of x and like say it is y. Now take the bitwise end of x and y, like take the bitwise end of this x and y, and subtract. Third is subtract this bitwise end of y from x. Okay, so the bitwise end of x and y, subtract this particular value from x. Okay, that is x and y is nothing but the 2's complement of y. After you do this, you would be getting your rightmost set bit unset. Okay, so we can take an example also. Okay, example, suppose we are talking about 5. 5 is nothing but 101, and now suppose if you want to unset this particular bit, what we can do is we can take the 2's complement of this. So the 2's complement of this, so if you are talking about the 2's complement, 2's complement is nothing but 1's complement plus 1. So the 1's complement of this thing would be 0 1 0. Okay, this is 1's complement, and we would be adding 1 to this, so that is 0 plus 1 is 1. Okay, so 0 plus 1 is 1, 1 plus 0 is 0, 1 plus 1, 0 is 1, and 0 plus 0 is 0. So this would be its 2's complement. Okay, now if we would be subtracting okay, so we have done some mistake. So the 2's complement, the 1's complement of 5 would be 0 1 0, and then we would be adding 1 here, then it comes out to be 3. So it should come like, what would be the parent of 5? So the parent of 5 would be 4. Okay, and the parent of 5 would be 4, and the binary representation of 4 is 0, 1 0 0. In that case, this rightmost unset bit is set. Okay, so now what we have to do is, now this is my 2's complement. Okay, so this was my 1's complement, and we have added 1 to 1's complement, and this is nothing but my 2's complement. Now we have to subtract my 2's complement from my 1's complement, that is 101 minus, and it is not a simple minus, it is a binary subtraction, and you would be getting in that case you would be getting it should be 2, and here you would be getting 4 as your solution. Okay, it should be 0 0 1, and you would be getting 4 as your solution. Okay, so that is your parent. So in that case you would be definitely setting your rightmost set bit. So you have to take your 2's complement, and 2's complement is nothing but 1's complement plus 1, and you would be taking the bitwise end of this, and you have to subtract the bitwise end of this. Okay, so we have made one mistake and we have to rectify it. So this is its 2's complement. Okay, so we had made some mistake is at this point. So this was its 1's complement, 1's complement plus 1 is 2's complement, and the 2's complement comes out to be 3. And now we have to take the AND of this 3, 0 1 1, we have to take this AND of this 3 with the original number, and the original number is 5. So that comes out to be 1 and 1 is 1, 1 and 0 is 0, and 1 and 0 and 1 is 0. So this is the 2's complement, and this is the AND of the original number and the 2's complement, and then we have to subtract this number from x, and x originally was 101, and then we have to subtract 001 from this, would be 1 minus 1 is 0, 0 minus 0 is 0, and 1 minus 0 is again 1, and we are getting 4 as our parent. Okay, so this is definitely what we should get, because if we unset this rightmost set bit, we are getting 100. Okay, so these 3 steps we should follow to get the parent of any number x. Okay, but we don't have to like manually take the 2's complement and then we have to like do everything. We don't have to calculate the manually calculate the 2's complement, because suppose if x is my number, and if we are taking the negation of this, that is minus x, if we are taking the negation of this, then this minus x would be storing the 2's complement of x, because in system this minus x is stored as a 2's complement of x. Okay, so instead of manually calculating the 2's complement, we can just write as if we have to find the parent of x, so the parent of x would be x minus x and minus x. Okay, because minus x would be 2's complement, and we are taking the 2's complement of x with the original number x, and we are subtracting it from the original number, so that would be the parent of x. So we have to do this. Okay, so each time to find its parent we have to do this, and after getting the parent we have to do it recursively, because if you follow this tree, if you are at 7 and if you have to calculate the sum of 0 to 7, in that case what you are doing, you are first at the point this 7 and you are taking the sum that is stored at this point, and then you are moving to its parent, and then you are calculating this sum, and then from this point you are moving to its parent. So it should follow a while loop, and using that while loop you have to continuously calculate the parent of upcoming node. Like if from this node you can reach to this node, and then from this node you have to find the parent of this node, and then you have to move at this point, and from this point you should find the parent of this particular node, and you should move to this point. Okay, so the base condition would be the 0th node. Unless you reach the 0th node, you have to like keep tracking back the parent. So this is how you are going to query the things, and what you can do to update. So this is the complete thing is about querying. Now what we have to do the update. Okay, so what we have to do for update. So suppose if we are talking about the update, in the update we would be mentioning some index number and some value x. Okay, so suppose if we are mentioning some index and some value x, then what would happen? So we like in that case, if this is our given array, and if suppose this was the index, we are updating our value as x. Now we have to update the corresponding bit array also. Okay, the corresponding bit array would be affected. Okay, so it should update this index in the bit array, and it should also update all the like all the child indices also. And suppose how you are getting the parent indice, so we are getting the parent indices by subtracting this particular value. Okay, this uh, bitwise AND of the original number and the 2's complement of the original number, and subtracting this from the original number. So that was the parent of x. Now how we can get the child of x, or like what particular nodes? What do we mean by child? The child doesn't mean the immediate child. The child means the number of nodes. Suppose if we are updating the x node, then what are all other nodes that is going to get affected? So that we can calculate just by replacing this sign. Okay, instead of x minus we can just put a plus here, and that would be giving me the node, the immediate node that would going to get affected. Okay, and after getting this parent of x, then some other nodes would be getting affected. So we have to find like from this value we have to move forward also. Okay, suppose if we are from x and we are calculating the y. Okay, and the y is nothing but this particular value, and after getting a y we can also find a y prime by using the same formula, unless this y reaches to the complete index, that is y is less than equals to n. Okay, so we have to do this, we have to do all these. Okay, so now in our data structure what we have to maintain, we have to maintain two operations. One is find, okay, which would be finding me the sum, or say GetSum would be a better function name. Okay, and in that we would be passing the index whose sum is required. Okay, that index means index x means we will be finding the sum from all the way from 0 to x. Okay, so this is what we would be doing in the GetSum function. Okay, and other function would be update. Here we would be updating a particular index by a value x. Okay, so these two functions we know, and like we have to use the while loop to continuously get the parents. Okay, so let us implement this. If anyone having any doubt, please mention in the comment section, otherwise I am going to implement it. Okay, as we are running behind time, so we have to implement it. Okay, we can declare n, and we can take it here, and then we can just take an array which would be storing our input array. Okay, and we can take this array as our input. So this is taking our input, and then we'll be processing some queries that we'll be discussing later. Okay, and we can take a vector bit. Okay, we can just take a vector bit which will be storing our binary index tree. Okay, so this is nothing but and we should initialize with it, we should initialize this thing with 0. Okay, so this is our bit, and then we have to like we have to maintain two function. One is uh, update function, so that would, the return type of that would be void, and that is int index, and the other value is int. So this is index, and we have to also pass a value that we have to update at that particular index. And then what we have to do is we have to run unless this particular index becomes greater than this n. Okay, and at each point what we will be doing, we'll be finding all those indices that is getting directly affected by this particular index. So that is nothing but we would be adding the index, the bitwise AND of the index and the minus index in the current index. Okay, and that would be giving me the all the nodes that is getting directly affected by this. Okay, and at every point we should add the value that is getting updated at this index. Okay, so this is nothing but x, because if we are updating x at some particular index I and d, in that case some number of nodes would be getting affected, so we have to reflect that particular updation in all those particular index. Okay, so this is what we are doing in this. Now after that we have to make other function, that is int GetSum. Okay, that would be giving me sum at a particular index, that is int. Okay, and we would be declaring a sum here, and what would be doing, we have to run a while loop, and at each point we have to sum this particular value, and then from this particular value we have to move it to its immediate parent, and then we have to sum up that value and then move to immediate parent, and we have to keep doing it our index unless our index becomes 0. Okay, so that's why this while loop, and at each point we would be adding the value that is present at this index in my bit array, and then I would be finding the parent of this index. And the parent of this index is nothing but we would be adding the bitwise AND of the original number with the negation of this number, and that is nothing but the parent of this. Okay, and then we will be returning this sum. And with this we can also make a function to give the result of the query, because this thing would be giving me the result of prefix sum, like from 0 to I, and to get a sum from L to R we have to take a sum from 0 to R, and then we have to subtract the sum 0 to L minus 1 from this. Okay, so for that we can maintain a function called query, so that would be query int L int R. Okay, and in that case we have to return the get sum R minus get sum L minus 1. Okay, now this is our complete function. We can take some number of queries as our input, and then we will be doing something like you can just take two integers int L to R, any integers you want to take, say int L comma R. You would be taking this L and R, and you can sum it up. Okay, see out, say query L to R. Okay, and you can output it. Now you can do this for some n number of times, so you can take a queue also for querying your data structure, and that would be Singh queue, and you can run a while loop on this queries, and you can calculate it for some queue number of queries. Okay, okay, now as we have not updated any value to our bit query or to our bit data structure, so we have to call the update function also. Here we have to update each value at this particular index. Okay, so I, as the bit is always one based index, because 0 index is the dummy index, so we have to make it one based index, and we have to pass this value here. Okay, now we can take some input like 5, and we can take some queries, and we can then check the sum of 1 to 3, say 2 to 5, say 3 to 4. Okay, a number, and let us check if everything is working fine. Okay, so we are not getting any output, so definitely we would be making some mistake. So we have declared our int here, we have taken our int. Okay, so let me check if the input we are taking is correct. So the input that we are taking is correct, definitely. Then we are taking LRQ, and we are taking the scene queue. So let me check if Q is correct. Okay, so Q we are getting correct. So definitely we have made some mistake in either update function or in GetSum function. Okay, so in the update function we are having this int as a result, and we would be adding this thing in our bit index, and we would be moving our index to index and minus index. This is fine, the update is fine. So what we can do is we can just check for a single query first. Before moving to the query, we can just check for a single query if it is working for a single query. and we'll be calling the GetSum function. So suppose the GetSum 5 we are calling. Now let us check what is the result. So we are not getting any result. So definitely the GetSum function is wrong. Okay, so we had made a mistake. So we have to subtract this thing. Okay, now it would work fine. Okay, so that is 15, as the sum of all the elements from 1 to 5 is 15. 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10, and 10 plus 5 is 15. Okay, so now everything is working fine. Now let me check for n number of queries. Okay, so what is 3? Okay, so we are printing this thing extra. No, the sum from 1 to 3 is 6. Yes, 1 plus 2 is 3, 3 plus 3 is 6. The sum of 2 plus 5 is 14. So this is 2. 2 plus 3 is 5. 5 plus 4 is 9. 9 plus 5 is 14. So this is also correct. The sum of 3 to 4, that is this 3 plus 4 is 7. So this thing is also correct. And at the same time, we can update a value also. For updating, so for that, suppose if we want to update the index, like the value that is written at the 5th index, to 7, then what we have to do is we have to like call the index function. We have to call the update function, and at the index I and d, what we have to update, we have to update this 7, but we cannot directly write 7 because it would be adding the 7 in 5. And suppose if you are updating, if at bit you have already stored at bit of 5, suppose if you have already stored 5, and now if you want to update the bit of 5 as 7, now you cannot directly update the 7 here, because the value that is changing to this particular point, you cannot directly add 7 to it. It would give you wrong result, that because 5 plus 7 is nothing but 12, but you want that bit 5 should store 7. So what you have to do is you don't have to add the complete number, you have to add 7 minus 5, the 2 here. So if you would be adding 2 here, you would be definitely getting 7 as your result. So you have to always add the difference here. So what you can do is you can update, say 7 minus what is already stored as the bit of 5, not the bit of 5, but what is already present at the array of 5. Okay, or array of 4. Why array of 4? And the index, say index, we have to update the 5th index. Okay, because this is the array 0 based and the bit is 1 based. So we can check now. The 2 to 5 should change by 2. Okay, 2 elements. Okay, so we have to comment it out. This is just for understanding purpose. Okay, and you can see that it has updated to 16, and you can check this also, 2 to 5. If you're checking the sum from 2 to 5, so that is 2 plus 3 is 5, 5 plus 4 is 9, and originally the 9 plus 5 was 14, but this 5 is changed to 7. So now you can say this 5 is changed to 7. So in that case 9 plus 7 is nothing but 16. So that's why we are getting 16 here. So our code is working fine. So this is all for today. Thank you.